Today, most satellite internet service comes from geostationary satellites, or geosatellites. These are satellites that sit at one point very high above the Earth and provide connectivity over a broad area. The main drawback of this setup is that you have a higher latency or delay in the signal provided because they're so far above the Earth. Satellites like this are also generally more expensive to produce and launch. Low Earth orbit satellites are much closer to the Earth and so have much lower latency or delay in their signal. The satellites are also smaller and less expensive to launch. Here you can see an animation that represents how the Starlink constellation operates. Again, you have a high number of satellites in constant motion covering all parts of the globe. And since they're so low to the Earth, that latency or the delay from the signal going from the ground to the satellite and back down to the ground is much lower than a geostationary satellite. We've learned a lot over the past year and have had a lot of fun testing out the capabilities of those two test satellites. We successfully communicated with ground stations to run 4K video and even play video games over the link. And we also partnered with the Air Force Global Lightning program to demonstrate how over 600 megabits per second of throughput to an aircraft in flight, which is super exciting for those of you who travel frequently. The bulk of our team working this project is based in Redmond, Washington, and watching today's exciting launch, as you can see on your screen right there. They're just as excited as we are in Hawthorne to see this rocket take off tonight. As I mentioned earlier in the webcast, this is our first launch of a production-designed satellite system as part of our effort to launch a next-generation broadband internet satellite constellation. This will be, fun fact, this will actually be the heaviest payload ever flown on a Falcon 9 rocket, weighing roughly 30,000 pounds. Each of those individual 60 satellites weighs about 227 kilograms or 500 pounds each. So while they're smaller than a typical communications satellite, they're still pretty sizable when you stack them all together. And that flat panel design maximizes space, allowing for a very dense launch stack, as you can see right on your screen right now, to take full advantage of that Falcon 9's launch capabilities. Starlink is also the very first Krypton-propelled spacecraft ever flown. Aside from being the native planet of Superman, Krypton also happens to be a nice blend of cost-effective and efficient propellant for ion propulsion. These ion thrusters enable the satellites to orbit raise, maneuver in space, and deorbit at the end of their useful life. The satellites also have a singular on-orbit solar array. This is one larger panel instead of two, which minimizes potential points of failure. Solar cells are standardized and easy to integrate into the manufacturing process. The Starlink satellites are also equipped with an autonomous collision avoidance system. To our knowledge, this is the first of any satellite constellation ever. The satellites use inputs from the Department of Defense's debris tracking system to autonomously perform maneuvers to avoid collisions of space debris and other spacecraft. This capability reduces human error, which allows for a more reliable approach to collision avoidance. In addition, 95% of all the components on the satellites are demisable, which means that when these satellites are at the end of their life, they will be naturally slowed by the Earth's atmosphere and ultimately be vaporized into dust as they re-enter. At 95% demisable, the satellites exceed current safety standards, and future iterative designs will go even further, shifting to a full 100% demisable material design. Also, while flying at a lower altitude of 550 kilometers, we ensure that the satellites will quickly and easily demise at the end of their life cycle. Once they reach the end of their life, the satellites will utilize their onboard ion propulsion system to deorbit over the course of a few months. In the unlikely event that a propulsion system becomes inoperable, the satellites will naturally passively decay because of atmospheric drag within 1 to 5 years, which is significantly less than the 25-year industry standard for low Earth orbit, or the thousands of years required if you're at a higher altitude.
Stage 1 to startup pressures.
2 minutes, 15 seconds.
Falcon 9 configured for flight.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition, liftoff. Go Falcon, go Starlink, go USA.
Vehicles pitching downrange.
A few minutes, those Merlin engines at the bottom of that first stage will light up, and there they go.
Stage 1 entry burn has started.
That is the start of the entry burn. To happen shortly. That is second engine cutoff.
Back shut down.
It sounds like we may have confirmation that the first stage has landed. That is a shot from Of Course I Still Love You of the first stage of the Falcon 9 rocket for its third landing. This brief loss of signal was expected. We should be able to get that video back very shortly. Stand by.
Starlink constellation deploy confirmed.
And we have confirmation of deploy. You can hear the team in the background. This is an incredible moment for SpaceX. You can see those flat-packed Starlink satellites slowly gliding away from the top of the second stage. This is the highest number of satellites that SpaceX has ever deployed in a single time. There are no deployment mechanisms between those spacecraft, so they really are just slowly fanning out like a deck of cards into space.